Morning, everybody. My name is Dave Glover. I work for the U.S. Fish and Wildlife Service out of Carterville in Southern Illinois. I'm going to take Ron Brooks's approach and set a timer for myself because I also can talk too much. And Greg, if you need to pull the hook out, that's fine too. So I've been working on hydroacoustics for about 9 years now, specifically for quantifying abundance of Asian carp. And so some of what I'm going to show you is very early from my career up until now, but I really want to focus on the relevance of hydroacoustics to Asian carp management and control. So unfortunately, I won't be getting too much into the theoretical aspects of sound and water. I'll just dabble in it, but I really want to show how this has actually been used for management on the water. So before I do that, I just want to acknowledge the fact that a lot of this work has been conducted at Southern Illinois University through a partnership with Illinois DNR and has been funded by the Great Lakes Restoration Initiative. That's where a lot of this work has been developed, and we've used it at the Fish and Wildlife Service as well, but this is really where it comes from. Just a few key references for some of the stuff I'll be talking about. No reason to jot these things down, but this, these four references can highlight a lot of the technical aspects of this, as well as how it's been applied. What's easier is just email me at David_Glover at fishandwildlifeservice.gov. So today what I'm going to do is just give a very brief overview of what split beam hydroacoustics gear is. But I really briefly want to go through 3 different examples of how we've applied hydroacoustics for actual management of Asian carp. And so basically we'll go through some the more obvious ways of how people think of this as being applied is through actually estimating density, and then also real briefly just talking about how we use this technique to direct removal efforts in low density pools. And then lastly, I'll talk about how we've also used this as a risk assessment tool near the Electric Dispersal Barrier and the Chicago Sanitary Chip Canal. And then I basically just have one slide to talk about how the fact that this is an ongoing effort and we're trying to constantly improve this technique by going through current research that's being done right now, as well as some future ideas on what we're hoping to do. So again, what we're using is a mobile technique, so basically using a boat with split beam hydroacoustics. There is a misconception, probably due to this slide in itself, of what split beam hydroacoustics is. Biosonics actually created this slide, but actually the beam isn't split up in any way. And this is just a view of what the gear actually is. So what we have is a rotator that can adjust the beam left and right, up and down. We use that to control our angles to where we can have the one beam actually running parallel to the surface and another beam that's pointed down. So we're actually maximizing or increasing the volume of water that we can actually sample. And each one of those, each beam is emitted from 2 separate transducers. And so what is split beam if it's not splitting the beams then? So real simple, the split beam is actually probably better or synonymous with the word triangulation. If anybody's done telemetry where you are detecting fish at different locations, you know that you can triangulate that fish's position. It's the same idea with split beam hydroacoustics. You have different listening points on the face of that transducer. so we can actually tell based on the time that it's received where that fish is located in 3 dimensions. So we have not only range, but how far off axis from the center of the beam that fish is, so we can put it in 3 dimensions. Why is that important? If you think about the face of the transducer and where that's coming back, where that sound is coming back, we can basically tell where that fish has been detected multiple times. So not only are we able to get more accurate target strength of that fish, the loudest sound would be coming back to the center. So if it's off axis, we know we're going to be losing some target strength when it comes back because that sound is being deflected. So we can compensate for the fact that it's off axis, off the center, to be able to get more accurate target strength of that fish, which is going to give us better estimates of our size. We can also calculate swimming speed and direction even when we're moving. So it's not only 3D, it's actually 4D because we're moving at the same time. I know it hurts my head too. But from that, also we can get depth information. So there's a lot of information that we can actually gain by doing a mobile survey like this with the split beam technology. So this is just a slide of some hydroacoustics that we conducted in the Ohio River, just downstream of Clover Creek near Cloverport, Kentucky. And so just to give you guys an idea of what this actually looks like. So if we're in the Ohio River, it's basically shaped like a bathtub in a lot of the areas that we're sampling. So we're actually looking toward the shore where most of the fish are actually located. And so what that looks like is as we go across our transects, we're actually collecting data toward the shore and picking up all these little dots or streaks that are actually fish targets. From those target strengths, we can calculate the size or estimate the size of those fish. And for this particular survey, we were shooting out about 50 meters. The maximum range of this technology is 200 meters. But the limiting factor most of the time is the depth. So even if you're looking out to the side like we are, the beam will get intercepted with the bottom much sooner than that. So usually 75 meters might be the max that you'd be looking out. There are no consequences necessarily to the resolution, even when you're shooting out that far, because we're compensating all of that information for how far away it is and the signal loss that might be happening. So some of the data that we're getting out of this is, again, population density. We can do that at a various spatial scales. So maybe we're looking at an entire pool. We're maybe looking at specific habitats, tributaries, backwater habitats, small lakes. But also we're getting size distribution. We can get GPS locations and depth of targets of concern. The swimming speed and direction of travel, like I've already talked about. But I wanted to emphasize that this is not a standalone gear for most of these applications, with a few exceptions that I'll talk about briefly. But this is best as part of a multi-gear assessment of the fish community and the size distribution of that entire fish community. We're not able to tell what the species is, so we need to rely on the proportional information that we get from the fish communities to divvy up those targets based on their length. Okay, so let's talk about density estimates. So the density estimates that we get from hydroacoustics are used as inputs for a lot of the population modeling that we do. So not only are we getting density, but we're also getting size distribution. The reason that size distribution and information is critical is because a lot of the vital rates that we have in fisheries dynamics are size related. And I'll talk a little bit more about that here in a second. But the reason the modeling is important is so we can compare management options to, before going out there, we can compare things like where should we harvest and how much intensity is required Where could we possibly put deterrent technology or use other operations like gait manipulation to slow these fish down? Where would that best be located? And what's the required efficiency or efficacy that we would need in terms of actually seeing some population responses? So this is just one part of several approaches that we really need to evaluate effectiveness of these management actions. So I won't go in this in detail, but the type of habitat that you're working with will dictate the type of survey or transect design that you might want to use. This is from McNamara et al., where this is based on some data that were collected in the Illinois River. And so basically, we have a very shallow sloping shoreline, and so we can actually look out, and those beams, as they open up, are hugging the bottom as they spread and go farther out. So the first transect will be as shallow as we can get, maybe a meter depth looking out. And then we had to do a second one where we're a little bit farther out, just far enough out to where we're not overlapping that first beam that's coming out. So we usually do one loop that's 4 miles long on the near shore area, and then a corresponding mid-channel loop. And we would stratify our analysis based on where that data is collected. In some of our backwater areas, we do very similar things, trying to make sure that we're not overlapping and getting multiple overlapping our beams. Again, all of this would change based on the depth of the system and things like that. And things like tributaries, we're also able to do the outward-looking type of transects, but we usually only need to do one set of transects because we would be overlapping beams if we did another transect anyway. But it all depends. So this would be an example of the Illinois River on the bottom, where we do have this shallower sloping bathymetry, and then it'll get deeper. So the way we have done that is we have one very close to the shoreline, one farther out in mid-channel. In the Ohio River, though, again, completely different bathymetry. The fish, where they're located, is very different. There's very few fish right out in the middle at the surface. So we can actually point in with a single survey to get quite a bit of information. The tributaries of the Ohio River looks much more similar to that where we're looking out, where we could probably accomplish most of what we need with a single transect along the shoreline. So just to kind of give you an idea of how this data flow would occur for estimating density, we would first have some information about the community based off of standardized sampling that most of us are familiar with. Electrofishing, gill netting, multiple gear assessments will be best. From that, we have a length frequency of all that data that we collected. So that means frequency of fish at different size categories, right? And from that data, I think most of us all can agree, every gear is biased, particularly in terms of size. But we do know the species composition of that. And so we can take a particular size category and split that up into proportions of things like bighead carp and silver carp. Hydroacoustics then, we're using that information or conducting those surveys to process all this information to figure out maybe a less biased view of that length frequency. Again, all gears biased, including hydroacoustics. But this is going to give us a little bit more accurate idea of the length distribution. But again, we don't know the species composition of that. So we're using the information on the proportion of these individuals and applying that to this length distribution so we can get a better idea of density as it changes across the length distribution. So what's the value beyond just going out and using the gear that we all understand? We all know it has biases, but we are able to make relative comparisons across the system that we understand. So again, we're getting more accurate size distribution, which is going to improve our modeling performance for multiple reasons. As I said, we're getting better information about the size distribution where the certain sizes are going to be contributing to reproduction, for instance. There's going to be certain sizes that are only vulnerable to fishing in a size biased or size selective fishery. So all that information is going to help improve the performance of our model. This is very well shown with multiple types of hydroacoustics. Most fish are patchily distributed. So when we use regular catch per unit effort, where we're limited in where we can go, we can end up with a lot of zeros in our data. And so that increases the variation of our data. And that could take basically either more effort or more years to be able to show trends in our data. So we can actually improve our precision by using a larger spatial coverage where we can better define the variability based off these patchily distributed organisms. The other thing is that effort is not created equal. Anybody in here who's been on an electric fishing boat knows that it matters who's driving and who's netting. And so there's just inherent variability that's hard to control in these assessments. The volume that we're calculating, apologies, is more definable, equatable across all these systems. So comparing catch per unit effort in Ohio River versus Illinois River, we know would be very hard to do because of the differences in these systems and our ability to catch fish. But with hydroacoustics, they're now comparable for these nationwide type of approaches that we're hoping to get. Again, it's not without a cost. This equipment is expensive. It takes years of training to be able to do this right and get good estimates. I'll leave it at that. So another example, directing removal efforts in low density pools. This has particularly been done in the Dresden Island pool of the Illinois River. So that is this pool between the Dresden Island and Brandon Road lock and dams here. So it's a pretty short pool, but this is the most upstream pool with a presence front in the Illinois River waterway system. It's only 15 miles long, which is still a lot of river to be looking for fish. But with hydroacoustics, we can sample that in 2 days, the entire main stem section of that. It takes us about 2 days to sample. So you're really looking at a 1-to-1 ratio in terms of how long it takes to conduct the surveys and how long it takes to process those data. The other advantage of the Dresden Island pool and the Upper Illinois River system is that the fish community is actually fairly simplistic. And so what we see is once you get over 500 millimeters, the likelihood that those fish are Asian carp is pretty high. I wouldn't bet my daughter's life on that is an Asian carp, but I'll tell you it's not a crappie. And so basically we can have a high confidence that those are Asian carp. So we can use that information to make heat maps or do hotspot mapping with minimal community data requirements. So again, this is one of those exceptions where we don't have to have a ton of community data to point people in the right direction. So this is what that looks like. This is the Dresden Island pool from the Dresden Island Dam up to the Brandon Road Pool Dam. And this little arm right here is actually the Kankakee River. And so this was conducted in March 2018. Matt, you can correct me if I'm wrong, but I think these were done about every other month this past year. But what's interesting is we can see these higher densities in the Kankakee River, and that information can be given to people on the ground and point them in the right direction. In May of 2018, we still can see that there are some larger fish in the Kankakee River, but now we have a much higher density located up near the casino on Dresden Island, where we can point fishermen in the right direction to actually catch fish, not to gamble. All right, so risk assessments near the electric barrier. So for those of you not familiar with the Electric Dispersal Barrier, this is Lake Michigan, Chicago area. And basically this number 7 is the location of the Electric Dispersal Barrier. And that was preferentially located to block movement into multiple places where carp could access Lake Michigan. And this is what this system looks like. So this is Romeo Bridge, and then we have a sequence of low field arrays, electrical arrays that are meant to deter fish, and then the high field array, which are meant to incapacitate fish. And so there's a series here where we have, sorry I can't see that one, but there was one created here in 2002 that's demonstration barrier, after which we created ones that have a much larger options in terms of the operating output, basically, for the electrical output. So 2A is a set of low field and high field arrays that were built in 2009. 2011, we built a second one in 2011, barrier 2B. There are plans for another one to be made here. So again, redundancy is a good thing. Parasitic structures, I won't go into much detail there, but they're large woven steel structures that span the bottom of the river that help concentrate the electrical field and keep it from dispersing across the entire channel. Which apparently was a problem when these were first installed. Okay, so the barrier surveys that we've been doing, the Fish and Wildlife Service has been doing, are basically from Hansen Material Services, just up to the pipeline, which is just upstream of that demonstration barrier I pointed out. But this is about a mile-long stretch of river, and these barriers actually require regularly scheduled maintenance where we have to turn things off. But again, the redundancy is good, so we can switch things back and forth. And but there's kind of a space that could be, in between these barriers that you could, if you did it in the right order, you could possibly send fish on their way. So we basically are trying to kind of assess the risk in these areas to kind of provide just another source of information in terms of risk assessment. There are temporary power outages that can and do occur. Luckily, the demonstration barrier at the most upstream location has maintained continuous operation. So, but the objectives of this is to really determine presence and absence of fish larger than 12 inches. The reason that particular size has been chosen is because of all the sampling and thousands of hours of electrofishing and netting that has been done in that upper Illinois Riverway. That's kind of the smallest or largest Asian carp that has been collected within 50 miles or even more than that of the electric barrier. So again, we don't need necessarily community data to be looking for these large fish, which doesn't necessarily mean that they're Asian carp. It's just giving us more information with the high risk. We want to be as conservative as possible. So outside of that, we're providing accurate location information for possibly targeted removal if that's warranted. So we're getting both accurate GPS and depth information off of these fish. So again, the biosonics split beam transducers are being used that we've already talked about. But we're also using side scan sonar, which is actually a tow fish. It's not the commercial gears, which I will say, I mean, it's getting ridiculous how good those can be right now. But so this is actually a tow fish that's being towed at 1 meter, just below the surface. This actually has a much larger beam and gives us a better idea of what's along the bottom than what we're getting with the split beam transducers. Just to give you an idea of the coverage that we're able to get with these gears combined, the split beam will be shown here in the greenish turquoise color, and then the purple is actually, here if I can hide that. There we go. So the side scan is the purplish color. So we're doing like a cross-channel look of the Chicago Sanitary and Ship Canal where the electric barriers are located. So basically we have 8 meters depth, about a 50-meter channel width across it. So we're looking from west to east here. And so this first transect that we do is upstream, looking out from west to east. So we have the split beam that's covering the surface, and then we have the side scan covering the bottom area here. And so basically, we can't really analyze the data for the split beam once that bottom of that beam is intersected the bottom. So the second transect is conducted moving downstream, so we're just turning around, and we're actually getting, shooting across and filling in the bottom again with the side scan sonar. The last transect, we're turning around and going back upstream with the side scan only in this particular case to fill in these corners a little bit. It's not instantaneous. We know a fish can move around, but we're repeating this 3 times to try to increase our odds of seeing larger fish. With this combination, we're able to cover about 98% of the water column within the barrier area. I'm not talking about below the barrier area. I haven't done the calculations for that percent coverage. But with the split beam alone, we're able to cover about 70% of the water column. But again, more toward the surface. So this is just a map that we're able to generate where we're actually able to show where larger fish are actually being detected. Again, we're doing that survey 3 different times, so we can say, which survey they were actually seen in, and be able, because we could be counting fish multiple times basically, so we want to be able to show that there's a difference within the electric barrier. This is Romeo Road, and this is Romeo Road up here on the other one. So this is below the Electric Dispersal Barrier, down at Hanson Material Service Corporation. And so we're able to point people in the right direction where we've seen fish. The other things we're able to do, I have a R script that is automatically able to calculate things like fish density below the barrier and within the electric barrier. And this can help basically put in context. Is there an increase? Is there a decrease in the number of fish relative to these past surveys? The other things we're able to do is show the volume of water that we're sampling. This is more or less kind of a data quality type of approach to be able to say, we're consistently doing the same area that doesn't fluctuate a lot in terms of its depth. So we're able to show how consistent we're able to get, but this also can change if we're going further downstream, further upstream, depending on what the Illinois DNR would like to see with the Army Corps of Engineers in terms of our sampling strategy. We're also able to show the angles that we're able to maintain, where it basically the darker blue line is showing what we'd ideally be maintaining to maximize our coverage. But this again is just showing us something about the data quality. Was it really rough out that day to where our angles were all over the place? Was somebody not paying attention and it went up, completely went the wrong direction? But again, this can help kind of give us an idea about the quality of the data being collected. So basically, the last slide is the big part of the current and future approaches to research is really to quantify and incorporate uncertainty across that entire process into our density estimates. There's certain relationships, for instance, the target strength to body size relationships. There is uncertainty in that that's not being incorporated right now. It's just assumed a certain function that has no error around it. We know there is, so we're actually using tethering fish out in front of our transducers to be able to get at the target strength to body size relationships specific to Asian carp, but also comparing that to some of the other fishes that we might be seeing. And the other thing that we'll be doing is basically getting a cooperative agreement to SIU to look at some of these fish in free swimming applications, like in ponds and things like that, so we can understand the variability of their target strength and the orientation and how that might affect it. And so this is kind of one of the experiments that I helped do when I was actually a postdoc at SIU. And what I will say is, if you ever do these experiments and someone says, oh, can I put like caged striped bass on the side of this while you're doing your experiment, say no. Because every time they come out and feed these things, catfish show up. And they block the signal for everything you're trying to do. So this was a failed experiment, not because we didn't try hard. So anyway, Greg, if there's any time, I know we got started a little bit late, but so if anybody has any questions.
Dave, are they working on improving the post-processing speed for the hydroacoustics data as HIPAC, or anybody getting into the works closer to real time?
So the question was about the processing time and whether there's been any efforts to speed that up. There has been efforts to speed it up. The main processing software that we use is EchoView, and we've been doing a lot of things to automate some of those analyses. There is danger in automating some of that, as you know. Treating things like black boxes can be fairly dangerous, and so we want to make sure we're doing it right. But as far as real-time analysis, Biosonics does have an application. It's mainly meant for downlooking. Once you turn these things on their side, it's a whole new ballgame in terms of being able to define the actual area that you want to analyze. Downlooking, it's very easy to pick out where the bottom is. When you're looking out to the side, it's barely grazing that bottom in these systems, so it's just not as hard of a return, and that's probably the biggest downside of trying to automate some of those processes. We're trying to do that, yeah. But in general, I would say most people don't understand that for the single target detection and saying where fish are, a lot of that is already automated with algorithms in the program. And Rosalie can attest that that's not perfect. We make a lot of corrections to that through manual editing. Thanks, everybody.